show was N-glycosides. This is also my own personal bias here. So if we were to take something like, we'll just put put this hydroxy group down. So let's make this one deoxy. Hydrogen here. I have a sugar like this. So this is deoxyribose. And if we were to react this in the presence of acid with some other nucleophile, let's use a nitrogen nucleophile. And I don't expect us to memorize these structures, just trying to wow everyone with something. But let's use something that looks like this. And we have a lone pair of electrons on this nitrogen here. And if we were to react this in the presence of HCl, we would end up getting a mixture of different stereoisomers in one position. But what we would see in terms of our mechanism is we could protonate this, which is the anomeric carbon. It's going to take off. We'd have a resonance stabilized carbocation. Then our nucleophile could attack. And we'd actually end up with both stereoisomers. I'll just draw one of them. So we have all of this, deoxy. And we'd form a N-glycosidic link. Something like this. And then make more clearly show that that's deoxy. And this is, for example, this is deoxycytidine. So it's the C in the DNA. Then if we phosphorylate here, you have deoxy-CTP. So this is one of the building blocks of DNA. And actually these nucleic acids, these nucleosides, can actually be formed by this sort of chemistry that's just like what we're seeing now. There's two ways actually to make the nucleic acids, but one way is actually you take this ribose and then you just pop on this nucleobase under some sort of an acidic condition, and this is going on biochemically. So it's kind of interesting that you can take these reactions that we've been discussing, and you'll see these in the biochemistry as well. And this reminded me of one thing, a little bit out of context, but I wanted to slide up for a second in response to a question, is when reviewing this material, and I think you'll see this a number of times this semester, and we probably already have, is we're trying to build up the complexity. We see, first of all, a mechanism where we take something like our common reagent, such as acetone here in the top I'm highlighting, let's say methanol. And we can draw a mechanism where we form the hemiacetal and the acetal, say, under acidic conditions. And that provides the fundamental mechanism. And then we apply this to something that's structurally more complicated, like with glucose. So we have all of these different functional groups, and we have selective reactivity at this anomeric position. But mechanistically, I don't know if I can show them both in the same here. The idea of the mechanism here in this acetal formation is the same as what we see at the top here as well. So what I encourage people to do is not to memorize all these mechanisms, but to go through this basic mechanism, and basic doesn't mean easy. Basic also doesn't mean the conditions, but simpler mechanism, that's maybe a better way of saying it. Then apply those ideas to the more complicated structures. Okay, I think that's one way of organizing. If it works for you. Okay, so now I'll save some space here. We want to consider a few more reactions with these carbohydrates. And one is to remember if we had an aldehyde or a ketone, we use an aldehyde, and we wanted to turn this into, say, a primary alcohol. This was an example of a reduction reaction. We might use something like sodium borohydride, NaBH4, and we saw in water or ethanol. So we can do the same thing with a carbohydrate. We can take our favorite glucose again for the 100th time. It's kind of wavy, it looks like there. And if we were to treat this with sodium borohydride, in water or ethanol. We'll just do it in water. It's probably more soluble. Nothing is going to happen to all of these hydroxyl groups. All we're going to end up doing is reducing that top aldehyde. So all this stuff stays the same. It's the problem with writing it out, is that we have to rewrite all this. Those are close together. And all that's happened is at the top here, we reduce this aldehyde down to an alcohol. So this was our D-glucose. But actually, it's very interesting, the name of this carbohydrate is D-glucatol, otherwise known as D-sorbitol. And this is one of those artificial sweeteners. And actually, I didn't do my homework to see if this is one of them, but you're probably aware, like with some of these artificial sweeteners, you can get away with a lot less than you can regular sugar, just because our taste buds are so sensitive to them. I forget if it was this one or not, whereas it's something like our taste buds are maybe more than 1,000 times more sensitive, so you can get away with using 1,000 times less of the sugar. Oh, it still tastes good though. I'll scroll up, try to leave that on the screen. So that's a reduction reaction. In addition to reduction, we can have it's 27 oxidizing reactions. So we're not really talking about mechanisms at all. And something like this is, I guess we have to use glucose again. Probably should have used a shorter sugar. A little longer. So glucose once again. And you may have seen something like this before, where you can take silver oxide and ammonium hydroxide, and there's some other reagents as well. And what we end up doing is we oxidize, and I just drew the product right here, so sorry, I need to correct this in the top. I'm going to erase this. We start with our aldehyde. I gave it away. And what we're going to do is oxidize this to a carboxylic acid. So we're going from an aldehyde to a carboxylic acid. Nothing else here changes. These are mild reagents, and so we're not oxidizing any of the alcohols, only that more reactive aldehyde. And this reagent here, I don't expect us to memorize, I just wanted to be aware of it. This is known as the Tollens reagent. And this is the one you may have done this or seen a demonstration of this, where you can take an aldehyde and you treat it with the Tollens reagent, and it deposits silver on the surface of the test tube or whatever it is that you're using, and so it creates a mirror, which is kind of neat. And these here sugars, it's a little bit confusing sometimes, but a sugar that can be oxidized is known as the reducing sugar. So a lot of times in the discussions, sometimes people will be talking about, is a sugar an oxidizing, is it a reducing sugar or not? And a reducing sugar is one that can be oxidized, which means it reduces something else. Because remember, if something is reducing, something else is getting oxidized. And where this actually comes into play, let's scroll this up a little bit, might be something mild. We can take back to I'm just going to draw a Hayward structure. Our glucose, what you'll notice is that this is the cyclic form, squiggly line for this anomeric form. This is in equilibrium with this open chain form. This is almost the last time we're going to draw this Fisher projection. So that if you were to take glucose and mix it in water, it's actually an equilibrium between these two forms, the cyclic and the acyclic. So that if you were to treat this solution with this Tollens reagent, like the one above, it's going to act as a reducing sugar, because some of the time it's going to be in the aldehyde form, so it could actually be reduced. That a difference is if you take something now and make this glucose a glucoside, so where all this stuff is the same. But now let's make this a methyl group. This is going to only be in a cyclic form. So this structure is not in equilibrium with an acyclic form, because we'd have to have this group lead in this case. And so this is a non-reducing sugar. So a little bit more of the terminology, that one. We'll see.